Alright, hello everyone and welcome. So in this video series, we are going to learn another application of integration. So this application is called hydrostatic force. So hydrostatic force. That means to understand this, think that you have some kind of an object inside a liquid. Okay, so let's assume water. Okay, so you have some kind of an object inside water like you see in this picture. Now what you want to calculate is the force acts upon on this object because of water. Okay, so that's what we are gonna find out. That's what we're gonna learn, how to calculate that hydrostatic force using integration. And also then after that we can calculate hydrostatic pressure after we know the force. But for this discussion, for this video series, let's only focus on hydrostatic force. Okay, right. So to get started, we actually start with Newton's second law. So F is equal to mg. So G, let's acceleration, let's think G as the acceleration. Well, actually it's gravity. G is gravity, m is mass. Okay, so we can assume that mass is given in terms of kilogram and gravity is given from meter per second square. Okay, now we can say mass is actually the mass density times volume. So V is volume and rho here is mass density. And furthermore, volume, we can think for a simple object, it's the area of the cross-sectional side, cross-section, and then the depth or the height. So D is the depth and then A is the area of the cross-section. So overall, we can write, when we substitute rho AD for M, we can write force is equal to rho GAD. Okay, so that's force. Now to talk about units, rho is mass density, kilogram per meter cube. Okay, mass per unit mass per volume, right, per unit volume. And then gravity is meter per second square. A is area, so that's meter square. Depth is meters. So all these together, we are going to get kilogram meter per second square, which we can say Newton. Okay, the units Newton. Right, then the force is measured using Newton. Right, so let's remember this equation and let's see how we can actually use this equation to solve a problem, a simple one. Okay, still we don't deal with integration. We'll learn that in a few minutes. Right, so now in this question we have a tank. Okay, a cubic tank that's 4 meters wide, 3 meters tall. Okay, and then they say that this tank is filled with water. Okay, so the height of the tank is 3 meters and it's 4 meters wide and 6 meters long. So these are the dimensions of the cubic tank and it's all filled with water. So they have given us the density, the gravity. Now what you want to do is to find the hydrostatic force on the bottom of the tank. Okay, the force created by the water inside the tank on the bottom of the tank. So the equation is F is equal to rho GAD. Now this is pretty simple. Rho, the density is 800 times gravity is 9.8, area of the bottom. Okay, so the bottom area is 6 times 4, 24, and D is the depth. So depth of water, so the water is filled in the tank. So from the top of the tank to the bottom, the height is 3. So if you multiply all these 3, we are gonna get all these 4 quantities, we are gonna get the force, okay, from Newton. Right, so that's a simple problem. Now this is a simple problem because the depth doesn't change. Okay, now imagine this is an important concept to understand. Think about you are inside a perfect cubic room. So if you're in a perfect cubic room, the height from the bottom, from the floor to the roof, top of the room, it's always same. Okay, so like here it's 3 meters, it doesn't change. If you calculate the height at different points, it's still 3 meters because it's a nice perfect uniform cube. Okay, so that's why this problem is simple. Now look at the second part. In the second part, they ask us to find the hydrostatic force acting upon the 3 times 4 side of the tank. So that means this side of the tank. So if I draw it separately, you want to find the pressure or the force created by water on this side of the tank. Now, how do you do this? Now, here there's a problem because the depth changes, right? Because think about this. If you take different points, okay, here the depth is different, right? Depth means from top to this point, the height, maybe it may be 1 meters, who knows, right? So here maybe it's 2 meters. From the bottom, it's actually 3. But in the part A, it wasn't a problem because if you think about the flow, if you take any point in the flow, from that point to the roof, as I said, the height is 3. It doesn't change. But here, if you think about a side of the wall, then if you take any point, several points in the side of the wall, several different points, you might find that the height from the top to that point is different in different locations. Okay, so depth is changing. So how do we find the force in this case? So it's similar. This is where integration comes into play. So the idea is similar to something that we did with area, volume, and arc length. What we're going to do is we are going to divide the region into slices. Okay, so here rectangles. Okay, small rectangles. And these rectangles, we are going to keep the width same. So delta y. Okay, just like we divided the area into several rectangles. Okay, right. So the width is delta y. That's kept uniform. Right. Now we are going to mark a 0 level. Okay, so we can mark a 0 level from anywhere. So I am going to say bottom is my 0 level, or like x-axis, that's my 0. You could make the top to be the x-axis 0, but it would be inconvenient. Think about this. Then you're dealing with negative numbers. If you put 0 here, bottom part, then it's negative. So rather than that, I'm going to put my 0 on the bottom. So you have to decide 0, where you're going to put your 0 in your picture. Okay, that's very important if it is not given to you. Right, then we are going to say from 0, the slice is at yi height. Okay, now yi, the reason is that this slice changes. We are only taking a one particular slice. This is like the ith slice. Okay, so like it's like the 4th, 5th slice. Okay, because we are going to have infinitely many slices in this region, right? That's the idea, just like rectangles. So this is just a one particular slice. We call it the ith slice. Okay, right. So the total distance, remember, it's 3. So those are the information that we need. Now remember, 3 things to do. Okay, so take the picture, draw a slice, width is delta y, then mark the 0 axis, and then from there, from 0 to slice, mark the distance as yi. Okay, that's how far the slice is from 0. Okay, that's important. I'll show you why. Right, now I'm going to calculate the force on this ith slice. Okay, not on the entire thing, but on the ith slice. So it's rho g. What's the area? Think about this. Now, area of the slice. Okay, so the length of this slice is actually 4, right? Because you are working on the 3/4 side. So it's 4 times delta y. Right, that delta y is the width. So area of a rectangle is length times width, so 4 delta y. And what's the depth? Depth means how far the slice is from the top of the water, right? So they are asking for this distance, so it's 3 minus yi. Okay, that's why it's important, this yi, how far away this slice is from the 0 axis. So it's 3 minus yi. So it's here 3 minus yi. So the force, I'm going to write it in a better organized way. So it's 4 rho g 3 minus yi delta y. Now that's the pressure on one slice. Now we want to find the pressure on all the slices and add them up. That's how we find the pressure, or actually the force I should say. We want to find the force on every slice and then want to add them up to find the force on the entire thing, right? So if you have n slices, I can say I goes from 1 to n, first slice to the n slice. We are going to add 4 rho g 3 minus yi delta y. Okay, so this is the force acting upon the entire side using n number of slices. Now if you want to get a more accurate answer, what do? You keep increasing the number of slices that you take. You let n goes to infinity, right? Okay, so this is where you get the definite integral. It's 4 rho g 3 minus y delta y is dy, and you're integrating from where to where? So from bottom to top, 0 to 3. That's the integral. This integral will give you the force acting upon that side of the tank. Okay, 3 by 4 side of the tank. So the idea is you divide it up into slices and then add the contribution. So it's an infinite summation. When you take the limit, so finite summation, you take the limit, okay, n goes to infinity, then you get the integral. Okay, right, so let's do this. So I'm not going to solve the integral. That's not the point of this lesson. So I'm only focused on setting up the integral. Right, so let's find the pressure on the 3 by 6 side. So it's 3 by 6 side. So again the idea is same. Draw the slice, and this is delta y. Below I'm gonna mark, that's my x-axis. So this is yi. So it's going to be, so I would recommend you to first write the force on a one slice. That will help you to get started. So that's going to be rho g. The area is now, the length is 6, so 6 delta y, and the depth is 3 minus yi, right? Depth is this, so 3 minus yi. So that's the force on one slice. So if you write the integral, you are integrating from 0 to 3, 6 rho g 3 minus y dy. Okay, so this is the integral that will give you the force acting upon the 3 by 6 side. Okay, because of the water inside the tank. Okay, right. So yeah, that's how you set up an integral to find force acted by water acting upon a certain object. Okay, right. So now in the next video I'm going to solve a couple more examples and show you how to set up the integrals.